Well, hello friends. Welcome back to browser hacking. Today, we are going to start on something that I have been wanting to do for a long time, which is a bytecode for the JavaScript engine in Serenity OS. So until now, the JavaScript engine has worked by parsing JavaScript into an AST and then just walking the AST in order to execute the code. So if we make a simple JavaScript test program here, like, I don't know, just 1 plus 2, then we can run the JS command, it's here, with -A to get an AST dump. So this very simple program generates an expression statement that has a binary expression with a literal plus another literal. And when we execute this program, we start at the root here, and then we just walk the tree recursively, evaluating every node as we go. And that's a very naive approach to language execution, and it has a number of drawbacks. For example, you end up using a lot of native stack to do this because of the recursion, right? That when we want to enter the children of a node, then we have to make a recursive call to those nodes and so on. And for that reason, very often when you are capturing an execution stack of our JS engine, it's many levels deep in AST recursion. And another issue is that there's a lot of sort of pointless busy work when doing AST evaluation because a lot of nodes don't really do anything. So you end up evaluating sort of empty nodes. And the solution to all of this stuff is to generate something better from the AST that is then more efficient to execute. And the first such thing that we can do is a bytecode. So basically, we want to turn our AST into a sort of assembly code, but our own made-up assembly language that targets the JavaScript virtual machine. And I've never implemented a bytecode VM, or anything like this before, a compiler. So this is all new stuff to me. I've been around these things. I've been around the JavaScript core bytecode VM when I worked on WebKit, but I never actually worked on the bytecode itself, other than I implemented like a compression algorithm for the bytecode once, but that didn't have anything to do with the content of the bytecode. It was more of a compression algorithm. So I'm very new to all this, so I will probably make some silly mistakes and stuff. Just bear with me as we figure this out. And I haven't really done any reading about it either, so we're just gonna jump right into it and see what we can fashion here. So I guess today I would like to be able to just execute this thing here. So we want to generate bytecode for this, and then have a bytecode interpreter that can compute the result. And let's see. So let's start by creating some files just to sketch this out for ourselves. So we'll make I think we'll make a new bytecode directory. And in that bytecode directory, we will have some files like maybe an instruction. And I think we're not gonna pack these well in memory to start out. Like we'll while we're just experimenting with getting things up and running, we'll just do something that doesn't compress, and then we can look into smarter, more memory efficient things later on. Because right now we just need to figure out how this should work. So I guess then we need some kind of a code block, probably a bytecode generator. And let's start with those things. And maybe let's make CPP files for those things as well. And then we can simply edit the file here. So bytecode instruction generator. All right. Oops. So I think we'll start with those primitives, and let's try to sketch some stuff out. So what is a bytecode instruction? Pragma once. So for our program here, I guess we would want this to turn into something like 1 + 2 would generate an add of a, I don't know, like a local. So we need registers or stack to store everything. Let's use registers because that's what I've seen before. So we'll just have like infinity local registers. Just that makes it kind of simple. So add local 0, local 1, save result in local 2. So, and then we actually need to do something like load 1 into local 0, load 2 into local 1, and then add them together, save the result into local 2. That looks kind of nice. Should we do Intel syntax with the destination first? I kind of like that actually. Yeah, I'm a fan of x86, as you know. Let's put the destination first. And maybe we'll use some big numbers here just to to make it a bit less confusing with the registers. I'm just thinking local 0. Maybe it would be useful to reserve a couple of registers for some stuff, like for calling convention, like return values could always be in local 0, for example. Also, why do we call them local? We can also just call them R. I don't need to overthink that. Yeah, so let's just call them R. And we'll do this. And then when you return something, you can put it into R0 maybe? Because that's kind of what you do on x86 is you return through the AX register. Yeah. Okay, so let's try to go from this to that. Yes. Okay, so let's invent the load and add instructions. Step 1, let's invent instruction. So we'll put this in a namespace here. Class instruction. I guess we will just do this as virtual classes for now, and then later on we can, as I was saying, we'd turn it into something more compact. But this is just to keep things simple. And then what do we need here? Like a toString maybe for printing. And let's make that pure virtual. And then we also need some kind of execution function, I guess. So like execute in, what is the execution context of a bytecode instruction? I guess it's like a bytecode interpreter. We didn't make one of those. Oh, we can just add one. Bytecode interpreter. Okay. Yeah, let's just add that as well. Okay. And then it could even be const. I think that would make sense, kind of, right? Because really you want these instructions to only modify the state of the bytecode interpreter and the corresponding like JavaScript global environment. But we don't want the instructions to self-modify. So I feel like const kind of makes sense. And then should we make a separate file for all of the opcodes? I think we're probably going to end up with quite a few of these. So let's make a separate file for them. Maybe we'll call it like ops.h. And actually, let's see what we put in there. So also, let's do the license header while we're here. We have these small license headers these days. Linus hasn't been here yet, but I'm sure he will he will catch up. So let's do this. All right, there we go. And yes. Instruction, sure. Oh, and let's do ops.h. So what do we put into the ops here? JS, bytecode. Should we do something like this, actually? That might be kind of nice. Maybe then we should call it op.h. Op.h is better. Okay, so op. So we have load for loading a constant into a register. So that's a final public instruction. And then just this stuff. And then we also need the execute. Oh, right, we don't know what a bytecode interpreter is here. Flip.js, forward, let's say. I think we need to forward declare these things, maybe at the bottom of this thing. So bytecode class block instruction interpreter and generator. What more did I add? Block generator instruction interpreter op. Okay, well, that's fine. What are you mad about? Well, that's okay, Client ID. Just chill out. It's gonna be okay. Yes. There we go. La la la. Interp. String to string const override. And how do you construct one of these? Well, it had two arguments. It had a destination register and a constant. So let's just say, well, I guess whatever a bytecode register is, maybe we can just call it that. Register and constant. So let's just use a JS value for now. And we can put these here. So destination, GST, value. Yeah, right. So what is a register? Maybe a register could just be, maybe it could simply be like a 32-bit unsigned. So we can do something like, I don't know, We don't have to get fancy with that. Like, if it's that, then that's probably fine. Although it might be nice to have some type safety for that stuff. So we can also just do something like class register and bytecode and dang it, where do we put this? Maybe here, register.h. Yeah, let's put it there. So what is a register? Well, internally, it's just a U32 and index, I guess. And then let's make it explicit so that you cannot just pass a number. You have to say register the number. Yeah. That's probably okay. We'll probably have to expand on this momentarily, but let's start with that. And then here we need access to that header, so we'll just register. Okay, and then the load instruction needs to remember the destination register and the constant. So dst and value and value. Okay, so that's our load. Yeah, we'll look at those implementing instructions later. Let's just also do the other one. What was the other one? Add has a destination and 2 sources. So that's a public instruction once again. Add register destination, register source 1, and register source 2. You can kind of imagine how these could be compacted into like a variable width instruction format instead of these virtual classes, right? Because it would just be like a leading byte for the opcode, and then like a byte for the register index, or I guess 32 bits for the register index, followed by the constant encoded as well. So this would be like 1 byte opcode, 4 byte register index, and followed by however many bytes value is. But let's not get carried away with thinking about more efficient memory representations, because we have much more fundamental problems of just architecting this whole thing. So let's do this. All right, private register. Okie dokes. And I guess same story here. We just need these guys. Okay, so now we have those 2 instructions. I feel like that makes sense. So how do we generate these things, and then where do we put them? Let's think about how we would generate them. So just based on how we currently execute the AST, we have every AST node, like here's an identifier node, which inherits expression. They all have execute, which is how we execute the AST, which is called execute on the nodes, and then they recursively call each other. So I'm thinking, what if we just do the same thing here, except for execute, we have something else in the base class, like a generate bytecode, something like that. generate bytecode, bytecode generator. So you just get the bytecode generator and then something like that, maybe. And oh wait, we probably can't make that. I mean, we probably don't want to make that pure virtual. So let's just have something here where we bail for unimplemented generators. Unimplemented or missing generate bytecode for yeah, right. And then we'll just say like to do, because we shouldn't get here. Okay. So the nodes that we do have in our AST are expression statement. Well, we have program, which is the outermost scope node, and then we have its children, which are expression statement, which has a binary expression child, and we have numeric literal. So we need to implement bytecode generation for these nodes. So I guess we can start with program, which is the class program, which inherits from scope node. What does program do when you execute? Calls execute statement because program is a statement. Sure. But program itself doesn't have the children though. So it inherits the children from thinking scope node. Yeah, so scope node has children and also has variable and function declarations. So I think if we just want to implement walking the children, then maybe doing scope node is okay. So let's see, generate bytecode. Because like we don't have to get fancy and do everything correctly. we just want to get something off the ground here. And let's see, and then also expression statement needs one. So we'll put that there, and binary expression, give you one of those. And finally, numeric literal, you also get one. Okay. And then what do we do in all of these? So we have scope node. Probably we want to call something on the generator that doesn't exist yet. So we had expression statement and binary expression, and finally numeric literal. So the numeric literal, maybe it's easiest to start with that one, because here we want to generate a load instruction. So we want to load one into a register, I guess. So we want to load, so we have a numeric literal that says, actually, let me update this program so it matches what I was sketching out. Right, so we have a numeric literal that says 100, and we want that to produce this load instruction. So I guess it would be something like generator dot emit a bytecode op load with the register target, which is well, we need to allocate a register, so I guess like destination is generator allocate register, maybe. So destination, and then whatever my value is, right? Because this thing has a value here. So we'll just give you that thing. That's fine. And then I'm just thinking, how do we communicate to the outside world what we just did? Because yeah, we allocate a register, but how does add know which one to use here? I mean, I guess we can just return it. So what if we just do like bytecode register like this? Or even like optional bytecode register, because maybe you don't always want to return one. Although if you don't care to return one, then you can also just use like R0 or whatever. Because whoever calls generate bytecode will know if there's some interesting output or not. Now I'm wondering, like, do some nodes sometimes produce an output and sometimes not? I'm not sure. So because of that, because I can't like think that far ahead, so I'm just gonna go with optional register. So let's see. And then we would simply return the register. I think that would make sense. And then generate bytecode, optional bytecode register. Yeah. Okay. Oh shoot, it overrides a member function, but it needs to be marked override. What a silly mistake. Okay. All right, sure. That feels reasonable. And then, what do we do with these other nodes? Also, what's wrong with you? A line of? Yeah. I think that's a Clang complaining. GCC doesn't have a problem with that. Although, well, actually, no. Maybe I'm wrong about that. Let's make sure that we have the declaration of bytecode register at hand. On hand? Yeah, okay. My bad. I was blaming Clang when it was not Clang's fault. It is kind of interesting though that like I'm editing the code with CLion, which uses Clang for code comprehension, and then we're compiling with GCC. So there are some instances where Clang and also the IDE says, oh, this won't work, but then you compile it with GCC and it does work. Because I've noticed that the GCC is a bit further ahead on stuff like C++20 support, or at least they have been in the past. So this seems fine. Then should we maybe come up with what a generator looks like? All right, let's see. Pragma once. Yeah. Okay. So name space JS Bytecode. So what is a bytecode generator? It is a thing which you can call allocate register on. So allocate register is a thing. And we also decided that emit with a type is a thing. So I guess it would be something very similar to like the way that you allocate stuff. Where you also just pass in the type, so you have like allocate without global object, and you sort of call it like this. So heap allocate without global object, you pass in the type you want to allocate, and then the arguments follow. So let's see. Here we instead want this to be emit. I don't know if we need to return anything actually. So we can just do like, I don't know, we'll just heap allocate it for now since it has virtuals. Make t, we'll call this ob type maybe. So we'll just forward the args. And we will append this somewhere. So maybe it goes at the end of the block I'm working on. I don't know. Append, move up, something like that. So I guess this thing needs to have a block, which we made a block.h, but we didn't put anything in it. So let's just, I guess we want to return the block. So let's keep it on the heap. So it will be an onPutter to block and block. And then block is something that we need to see here actually, because otherwise that's not going to work. Although I guess we can also do something like this. Append, move up, and then we can put this out of line, and then it doesn't need to see the declaration of block. Forward. We do need onPutter though. Yes, and for the register allocation stuff, I guess we can just keep like m next register. We'll just start it at 1. Yeah, I think that'll be okay. All right. Also, why did that look so goofy? Isn't it supposed to be like that? Yeah, it is. Wait, did I goof those up? No? Okay. Sidetrack. Let's see. So generator needs an append, which I did not declare. So void append. I guess a non-null onPutter to an op. To an instruction, actually. Oh, right. These are not ops, they're instructions. That's okay. Op is just a namespace where we put the instruction subclasses. So I guess a block consequently needs to hold a vector of instruction or something like that. Sure. So let's see. Generator append. Need to see that here. So the JS bytecode generator. mblock append move instruction. Sure. Oops. So then what else did we have? We also had allocate register, right? So allocate register. This will get very fancy. So next register plus plus. And we'll probably do something nice like this also. So like numeric limits U32 max. Yeah, we don't want to crash over the overflow border. So let's just be cool and do that. Register. Okay. That seems cool. And then what is a block? Let's just sketch something out here. Class block is, we said it was a vector of instruction. It's a non-null own putter vector instruction. Sure. So for that we need libjs forward and ack non-null own putter vector. Thank you. Thank you, C-line. Very cool. Append non-null own putter to instruction. There we go. Okay. Maybe we'll hide this actually and do something like create. Yeah, we'll make one of these things. Because we don't want anybody constructing this thing on the stack. That would not be so nice. But we can let you destroy it though. Let's see. Return adopt own new block. Am I overthinking this? I probably am. I just feel like I don't want to add a bunch of extra headers here, so let's just go to blocks EPP and put those in here. So block. So I guess a block will kind of correspond to a function or like a program. So this here would be one block, but then if you declare a function, we would sort of compile that function into a separate block. And then when you call that function, you're just calling a different bytecode block, I guess. I'm not sure. I'm not sure exactly how that would work, but I feel like you have to have some boundary. I don't know. We'll see. So I wanted the non-null own putter to block create. Right. Oh, and then we'll put that like that. And then the thing that actually mattered was the append function. Append move instruction. Done. Wow. Sophisticated. Yeah, that sort of makes sense to me. So let's see, what do we have now? We have a generator. Incomplete type instruction. Sure, let's address that. And when we generate the code here, oh, we need to see the generator. And we need to see the ops. Op. Okay. That's pretty sweet. And then for the other nodes, like for the scope node, we have a bunch of children. So like for auto, child, and children. Maybe like child dot generate bytecode. That seems like not much else to do here. Because what is when you execute a scope node, then you're just walking the children. Like the scope node itself, I mean, I guess what it does have is variable declarations. So when you enter into a scope node, you need to walk the list of variable declarations and function declarations that are part of that scope and instantiate some things. But I think since we're working with this test program that doesn't have any of that, let's not do that right now. But I think like later on, we might want to have something like enter scope or node or whatever that that does all of the setup of the things that are in that scope. But for now, this is probably okay. Oh, and then I guess we'll just ignore that for now. So void reg. I'm not a big fan of writing things this way, but that is the pattern that we have used elsewhere. So maybe it's such a mouthful because it returns optional, and optional is no discard. So we have to do something with it. And then what is an expression statement? I think it just has an expression, right? So yeah, so we really just need to can we just do this basically, like generate bytecode generator? Yeah, we can just forward to the expression. I think expression statement is not a particularly interesting AST node. So it is an example actually of what I was saying earlier about how some AST nodes are kind of just empty because this thing just forward to its child, right? So when you're walking the AST, you're paying the price of an additional nesting level in your recursion, but it's just calling through to a child. So by generating bytecode instead, once we're executing, we won't have to pay that cost anymore. So it's only a cost that you pay only while you're generating the bytecode. And then the binary expression. Oh, I guess we'll have to look at how the binary expression execute. Yeah, how does that work? So okay, so first we execute the left-hand side, check for exception, then execute the right-hand side, check for exception. So exception checks are interesting, actually, when we move to a bytecode, because I think basically what we can do is in our bytecode interpreter, where we dispatch all of the different handlers, we can just check for exception in between each bytecode. And then I feel like that will actually simplify execution logic quite a lot, because at the moment, everywhere here in the AST file, we have to check for exception, like if exception, if exception, if exception. And it's unpleasantly easy to miss one of those checks. I feel like one of the most common review comments on libjs code is there's a missing exception check here. So if we can get to the point where we have a bytecode interpreter where all of the exception checking is just done automatically in between the bytecodes, that is at least a huge reduction in like potential errors, we'd still have to do exception checks in runtime object implementations. But I do feel like this could be a nice way to just fold away a lot of potential bugs. So anyway, binary expression execute the left-hand side, then the right-hand side, and then look at the op to see what it is. So in our case, the left-hand side is a numeric literal, so that executes first, and then the right-hand side is a numeric literal that executes second, and then our binary op is presumably addition, right? So we just do add with the left-hand side result and the right-hand side result. So let's target only this specific scenario here and say if, or let's say, wait, what do we want to do? We want to generate code that first computes the left-hand side. So generator emit, or no, let's see, LHS register maybe, something like this. So generator allocate register, and then wait, no, that's not what I want to do. I want to, because it's this guy right here, and he's going to allocate the register internally and just return it to me, right? So LHS register is left-hand side, generate bytecode. Aha. Right, of course. And then the right-hand side is just generate the bytecode for the right-hand side. Oh, that is actually pleasantly obvious. And now we lost syntax highlighting for some reason. I'm just gonna, I think it's clangd died again. So let's just restart the IDE for a second. Clangd is so crashy. And I keep sending in these automatic bug reports, and I hope that they're useful to somebody. But man, I feel like it crashes 10 times a day or something. Sometimes much more, depending on what I'm editing. But we have syntax highlighting back, so that's good. So we have generated those two, and then we need to look at the op. So like switch op. And in our case, we had addition. So let's do something for that. In the default case, that's the to do because we need to implement all the other ops. But if it's addition, then we just want to produce this add node. So we need an output register. So I guess we need to do this auto DST. Should we call it test reg? Yeah, I don't like calling it just LHS here because it sort of conflicts with MLHS, which is the left-hand side expression node. So let's go with the reg suffix here just to be cool. So we allocate a register, and then generator emit bytecode op add with the destination, and then the source 1 and the source 2. Okay. Don't like that because because those are not right. Oh, those are optional. Oh, right. So I guess we have to verify that they are both, they have value here. So otherwise that's not gonna work. So we have to actually do this. can also use the operator star, I think. That seems okay as well. Yeah. All right. Yeah, that actually looks kind of okay. So then we have all of these nodes. So let's give ourselves a way, I guess, to dump one of these blocks so we can see what's in it. So just actually, let's, dang it, I want to have the number or the index at the same time, so let's do it this way. And let's just print it out. So maybe something like, I don't know, 3, followed by the instruction stringification, so index, and then m instructions I to string. Can I get that? I think maybe I didn't include it. Incomplete type act string. Wow, we're really bare bones here. All right, there we go. So we have this, we have that. When you create a generator, I guess it needs to instantiate that block in the constructor. So let's do that here. So generator, and block is make, or no, it was block create. Sure. And then how do you get the block? You make a generator and then you say, what do you do? I guess you have an API like generate, something like this, and then you give it an AST node. Okay, and then maybe we don't create the block here, but rather when you call generate, so like that. And then you get the block at the end, right? Okay, that makes sense. So maybe we kind of don't need to see this class constructor actually. So it can be something like that, and we'll make those internal. And then we'll make a generator for you here. Like, oh, and then we can actually do that in the constructor, right? Okay, and then node dot generate bytecode. I'm thinking we just need to see the ASD here, so. Generate bytecode node. No, not node. This. Is that not it? Wait, what don't you like? Oh, of course. Generator. Static. And then it returns in, again, the optional. Like, can we do that? This is so weird. I don't know. Why do we do this? Like, is this actually better than saying this? I am really not sure about that. Well, I don't want to get into thinking about that too much right now, so let's just plow ahead. Okay. And then maybe in JS-CPP we can add something for this. So wherever we do the capital A argument, we can have something similar, like dump bytecode. Dump the bytecode. Yeah. And how about D for dump or B for bytecode? I guess B is pretty nice. I don't know why this is capital A, actually. That's a bit weird. And Clang D has died again, I think. Dump ast. Where's dump ast? Dump bytecode. So wherever we dump the ast, which is at the top of parse and run, I guess we can just do dump. If dump bytecode, then let's actually generate the bytecode here, because we don't have a logical place to do that yet. So get to bump that thing. So we need to see the generator, and maybe that's enough actually to get started. Bytecode JS bytecode generator generate. Program? Is that all that we need? And I guess we also need to see the block then. So verify that we got a block, and then for auto instruction and block instructions. Oh no, we just want to say block dump. You don't have to do anything fancy here, actually. Yeah, right. Yeah. Let's see if that would compile. Feel like we've been writing code for a while here. AST CPP control reaches end of non-void function 2255. Here we get to the end without returning some. Oh, okay. So here we'll just return the destination register. Of course. Of course. And wait, I didn't implement any of the toString or execute virtuals, so it's probably not going to link. Right, we are missing vtable for upload, vtable for op add. Makes sense. So let's see if we can add those files. So libjs bytecode. Yeah, let's just start like that. Okay, and we're going to do the same thing for opcpp. Poof. Okay, so what goes here? String load toString, right? String add toString. And we also have void load execute and void add execute. All right. So just to dump them, we just need to do something here. So return string formatted load. And we had, for load, we have a destination and a value. So that's our destination, and our value is this. So let's say m destination m value 2. Need to convert it to a string. So libjs runtime value.h what's it called? ToString without side effects? Why doesn't anything work? What am I missing? Maybe I needed to include value.h there. And then I'm also now missing, wait, what is going on? So, okay, so wait, so let's do this first of all, just to simplify. And for add, okay, so including value.h seems to upset the universe because it expects something. Oh, well, I mean, it's part of the class actually, so I do need value.h. But maybe I can't include that without heap or something? Or heap cell, rather. I don't know, this seems messy. I don't know what's going on here. Okay. So we can dump the AST still, and then let's see, dump the, ooh, look at that. So there you go. That is the bytecode that we wanted to produce. Very nice. So that turned out pretty good. It worked. The first time we got it to compile, it printed the right thing. It just took a moment to get it to compile. Also, I don't know what's up with that. Okay, so I think the only thing remaining here is to make this execute somehow. So let's also do that by making an interpreter. So let's see, we start with the header and namespace JS Bytecode class interpreter. So not to be confused with the JS interpreter. This thing is kind of a sad class. This thing, I guess this thing will ultimately go away though, and bytecode interpreter will be the one true interpreter. But obviously there's going to be a lot of work before this can replace the existing AST walk. But yeah, I think bytecode interpreter is probably the most appropriate name. So let's call it that. Interpreter. And what do we have in interpreter? Well, I don't know. What do you call on this thing? Let's go to the call site and see how we would use this. So maybe dump bytecode will also for now test running the bytecode, or we'll make a separate thing for that actually. Let's make a run bytecode. Yeah, srun bytecode. So dump bytecode. Okay, so let's go with D for dump bytecode and B for run the bytecode. And then it's DB to dump it and run it. Dump and run. Anyway, dump bytecode. Oh, interesting. So I guess if dump bytecode or as run bytecode, then if we should dump it, then do this. If we should run it, then we need to make a bytecode interpreter and tell it to run this frickin' thing. Run bytecode. JS bytecode interpreter. Right, and oh, that shadows it. Okay, we'll call it the bytecode interpreter for now then. And run the block, I guess. Yeah, let's just do that for now. So you call the interpreter by saying run bytecode block, something like that. I don't really know what the state of the interpreter should be. I mean, we need a register file, so it would be something like a vector of value registers. Okay, all right, let's just grow this thing and figure out what we need to do. So namespace say JS bytecode. Run. And wait. What am I doing? What do we want to do here? We want to walk the instructions. Okay, so we need a program counter, and ultimately it needs to be able to jump to any arbitrary location. But for now, since we have such a simple program, we can just loop through the instructions one by one and run them. So let's keep it simple. So block block instructions. Let's expose it. So like instruction in block instructions. Yeah, let's just expose the whole thing. So like this. instructions. That's probably okay. And then instruction execute, I guess. So execute this interpreter. Oh, wait, shoot. I forgot to include JS value here also. Okay, so there's again that issue with that you need to get the heap cell as well as JS value. That's so... I think one of them has like inline functions for the other, so it's not very good, but let's not think about that too much right now. We are on a different mission here. Okay, there we go. And will you please just build? All right, so that runs the bytecode, but let's dump and run. So db. So presumably we are now calling execute and all of the ops. So let's make something happen when you do that. So when you execute a load, we want to take our value and chuck it into the destination. So I guess interpreter reg destination is value, something like that could be a cool way of expressing that. And then, or no, value amp reg. So you have to provide a register actually. Let's do something like that. M registers our index. No copy. Wait. What am I doing wrong here? I'm sure I'm doing something wrong. Invalid use of incomplete thing. Wow. Bytecode reg. All right. Invalid use of interpreter. Sure. Register has no member named index. No? What did I call it then? U32 index. Wait, what? Wait, where does the confusion start? Expected paren before index. U32 does not name a type. Oh. Aha. Nope, not that one. This one. There we go. And then we crash in vector thingamajig, presumably in the register accessor, because we never give the register file any capacity, or we never size it up. So maybe when you run a block, you would do something like registers resize to block register count, something like that. Register count. And we'll just keep that on hand. So register count. And oh, interesting. I guess when you we kind of like these things should be kind of internal to the generator actually. So we could actually use badge here. So bytecode generator. And set register count. Something like that. It doesn't have to be fancy. Then we can get those, and I think at the end when we finish generating here, we will do something like generator m block set register count next register, because that thing starts at 1. Does that work? I guess that works. So the 0 register is always going to be there because this thing starts out at 1. It's a little bit awkward, but maybe it will be okay. M block append, sure. And we forgot about the badge template, so let's get that. Okay, so now it runs, but maybe we should dump out the state of the register file after finishing a block. So let's print something here like interpreter bytecode interpreter run block address, I guess. And then at the very end, run block, did run block, and then for size t, registers size, just loop through all the registers, and the content. I think if the register is empty, then we can't call toString without side effects on it. So value string, let's say, if m registers I is, it's non-empty. If it is empty, then value string is empty. Yeah, let's do something like that. toString without side effects. Okay, so the 0th register, empty, sure, that makes sense. And then we loaded up 150 just fine, but I feel like the add thing didn't happen, presumably because I didn't implement it. So that makes sense. Interp. So here it just becomes a matter of doing interpreter.reg m destination is well, let's see. Let's do this. Result is add of msource1 and interpreter reg msource2. So let's compute the result before we assign it. Or maybe we don't need to do that actually. So interpreter, reg and destination. Yeah. That looks really, this looks so cool actually. Like it's so simple when you break things down to this level. It's pretty easy to see how you can go from this type of representation to native code if you want to do a JIT later on. But I think moving towards a bytecode is a very good first thing to be doing before we start thinking about JITting anything at all. So yeah. Is this going to compile? No, because add takes a global object, right? Which we don't have. So let's store it on the interpreter. I don't know, global object, global. I mean, it doesn't exist yet, but we'll put it down here. So global object and global object, sure. Return the global object, sure. Maybe we will require one when you instantiate the interpreter, because why not? Sure. Sure. Then, when you make one of these puppies, you just have to say, well, you can have my global object, bruh. And then, can we run then? Ah. Okay, so it works. That totally works. So we load, and then add. Fantastic. Okay, so I think we're going to commit at this point. So this will just be our first sort of step into this field. But I'm happy with the result. It's very, very simple, obviously, but I really like that we've done this in a way that doesn't interfere with the rest of the JavaScript engine in any way, right? So this is like completely on the side of the existing AST interpreter. The only disturbance really is that we have added some additional virtuals to AST nodes, but they don't affect the behavior at all of the AST interpreter. Also, my thermos is making a goofy sound, so I'm just adjusting that. Okay. So yeah, let's commit some stuff. Git add. And I mean, we're just gonna have to bring everything in actually, because we can't really, all of these things are depending on each other. So let's bring them in. Just thinking about the copyright headers. Let me just make sure to update those. Okay. Fantastic. And let's write the commit over here actually. So lib.js, start fleshing out a bytecode. A bytecode for the JavaScript engine. Right, so to This patch begins the work of designing or implementing JavaScript execution in a bytecode VM instead of an AST tree walk interpreter. It's still extremely it's probably quite naive, but we have to start somewhere. The basic idea is that you use a bytecode generator that you call JS bytecode generator generate on an AST node, and it hands you back a, well, let's say, bytecode block filled with instructions that can then be interpreted by a bytecode interpreter. This first version only implements two instructions: load and add. Yes. The interpreter, or the bytecode, is has wait, hold on. Each bytecode block has infinity registers, and the interpreter resizes its register file to fit the block being executed. Yeah, I think that's fine, and I mean, there are downsides to that, and we can probably improve it in various ways. And it's just I'm not super familiar with this field, so like I said, I'm probably making some silly mistakes here or something, but I think it's good if we just start, and then we can improve the design as we go, and as we discover what other things are needed. But this does seem like a good place to start. So what went wrong? Commit failed with error. Oh, is it the, oh, dang it. So, excuse me. I guess there's some pre-commit hook failing, and I can't see that in C-line, which is super annoying in this case. So let me make sure I don't lose my commit message, and we'll run the pre-commit hook, see what happens. What don't you like? What do you like? You don't like bytecode op-h because it lacks a license header. Oh, because it was goofy. All right, all right. So let's try again. Yeah, there we go. All right. So I guess I should actually, I'm going to amend this here. 2 new JS options are added in this patch as well. D will dump the generated bytecode. B will execute the generated bytecode. Note that that unless D and or B are specified, none of the bytecode related stuff in libjs runs at all. This is completely implemented in parallel with the existing interpreter. Yeah. The existing EST. Yeah, I think that's really good. Okay, so this will be the end of today's video. If you made it this far, then I thank you for watching. I hope that you saw something interesting, and I certainly find this a little bit scary because I'm venturing into new territory. But I think we have a decent base here and a lot of obvious places where it can improve, but you know, good start. So it'll be interesting to see where we can go with this. And yeah, thanks for watching, and I will see you in the next video. Bye.